I first invite M.V. Bhimeshwar, Dr. Major M.V. Bhimeshwar. He is the present President, ISA National, Additional Director of Government Medical College, Eluru, Andhra Pradesh, retired. Controller of Exams, NTR University of Health Sciences, Vijayawada. He was the registrar at NTR University of Health Sciences in 2019, Vice President of Indian Society of Pain, member Academic Council, KLE University, Belgaum from 2009 to 11, and Honorable Secretary, ISA from 2012 to 14. I welcome you, sir. I will invite you to the dais. Dr. M.V. Bhimeshwar. Invite Dr. Shamshad Begum, Professor and HOD of Anesthesiology, MES Medical College, Kerala. She was a former Professor and HOD, Government Medical College, Thrissur, Head of the Department since 2017 to 23 of MES Medical College, Kerala. She was Medical Superintendent, Government Medical College, Thrissur in 2016. She has been an external examiner of MD at various universities, DNB examiner of anesthesiology and emergency medicine. She has been an inspector for MCI, NMC, and a DNB assessor. She has 15 national and state publications to her credit, and she has done more than 100 presentations. She has a total teaching experience of 32 years. I welcome you, ma'am, on to the dais. I welcome Dr. Major M.V. Bhimeshwar onto the dais. He is the present President, ISA National. I welcome you, sir. Persons to introduce our speakers for the session. Speak about gas loss and anesthesia.
Yeah, good morning, everyone. I welcome you for the first session of this CME opening batsman, Dr. Gurudatta. He needs no introduction, wonderful person, and a very strict disciplinarian, ex-army. And I request Dr. Gurudatta to proceed.
Good morning, everybody. And first of all, I would like to thank all the organizers of ISA South. And also, I would like to bring greetings from my medical college. Presently, I'm working JSS Medical College and Hospital, Mysore. You all know that 1846, October 16th, W.T.G. Martin introduced ether as the anesthetic agent. And even today, October 16th, we celebrate as the World Anesthesia Day. And 2 years before, Horace Wells tried to introduce nitrous oxide as an anesthetic gas, but of course failed. But today also we are using nitrous oxide. And since then, we are using many gases in anesthesia. Say it can be oxygen, nitrous oxide, it can be even carbon dioxide, or even in all the inhalation anesthetic agents. So many gases we are using. And you all know that these gases obey gas laws. And since these gases obey gas laws, it is very important for us to know about these gas laws and to thorough with these gas laws so that we can be very safe to our patients. So there are many gas laws which are, every day we can use as far as our day-to-day anesthesia practice is concerned, like Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's hypothesis. It can be many other gas laws. And all these gas laws, I will not be able to discuss with you today because of only the time that has been allotted is 20 minutes. It may take even 2 hours or 3 hours to discuss about all the gas laws. So whatever the time that is allotted, I'll try to discuss about these gas laws. Let me discuss about the first gas law, that is a Boyle's law. So Boyle's law defined as the volume and pressure are inversely proportional to each other when temperature is kept constant. That is, PV is a constant. So what are the applications? Now, many times, when majority of the times we'll be using the central pipeline of oxygen, and suddenly if central pipeline of oxygen is, the pressures are dropping, and then we'll have to open up our backup cylinder. The backup cylinder that is always connected to our anesthesia workstation is E-type cylinder. Now I want to know how much of the oxygen that is available for me to use during till the pipeline oxygen is restored. So once I open the cylinder, then immediately I'll know that how much of pressure is there in the cylinder, in the pressure gauge. Now using Boyle's law, I can always know how much of oxygen that is available. How do I use it? Now a full oxygen cylinder, E-type cylinder, will have a maximum pressure of 2000 psi-G. And when I want to know as psi-A, that is an absolute pressure, so I'll have to just add 15 psi, that is the atmospheric pressure. Now I have 2015 psi-A as the pressure inside the cylinder. At atmospheric pressure of 15 psi, how much of oxygen that is available for me for use? So using again Boyle's law, P1 V1 is equal to P2 V2. All of you are very familiar with this equation. So I get about 672 liters of oxygen that is available for me. So that means when I open a full oxygen cylinder and I am using 3 liters per minute, I will be able to use this oxygen for about 220 minutes roughly. The second application of Boyle's law is, breathing. So when I take a breath, inspiration, I expand my chest, I expand my lungs. So once I expand my lungs, the volume increases, automatically the pressure drops. So once the pressure drops, a pressure gradient is created from the atmosphere to the alveoli, about 5 centimeters of water pressure gradient, and because of that, air moves into the alveoli. The opposite occurs during expiration because the lung recoils. Once the lung recoils, the volume decreases, the pressure increases. Again, the movement is towards the atmosphere. One more application is, for measurement of residual volume and FRC. These are the static lung volumes, the functional residual capacity and residual volume. So these static lung volumes will not be able to measure using our spirometry. So what we require is a body plethysmography. Again, for body plethysmography, we'll be using the Boyle's law for measurement of residual volume and FRC. The second law, that is the Charles law, this is volume and temperature are directly proportional to each other provided the pressure is kept constant. So what is the application? Like, one of the applications is for determination of inhalation anesthetic agents. So especially when we use Avogadro's hypothesis, because next I am going to talk about Avogadro's hypothesis, I can know that especially for example, sevoflurane. 1 ml of liquid sevoflurane, I know that it can give 168 ml of vapor at 0 degree Celsius or 273 kelvins. So when I know, because Avogadro's hypothesis is always standard temperature and pressure, that is standard temperature is 273 kelvins. Now I want to know how much of vapor I can use it at 20 degrees centigrade, that is the the OT temperature. So for calculating this, I have to use the Charles law. V1 by T1 is equal to V2 by T2. So that way, I know that 1 ml of liquid sevoflurane will give 180 ml of vapor. Next, the law is the Gay-Lussac's law. Gay-Lussac's law is pressure and temperature, their relationship. They are directly related to each other, provided the volume is kept constant. Now, how do I apply this Gay-Lussac's law for my day-to-day practice? See, one thing we always keep telling everybody that these cylinders, gas cylinders, should never be kept in sun, or they should never be heated up. So what will happen if they are kept in sun by accidentally, if we keep these cylinders in sun, the gases starts getting heated up. So once they start getting heated up, the pressure starts increasing. The volume remains constant here because the tensile strength of the cylinder will not allow it to expand. So because of this, at a particular critical pressure is reached, there is a chance that these cylinders may burst, and even they may fly off and then can produce collateral damage. So we all know that the safety relief devices are always there in majority of the cylinders so that this can be prevented. And especially one of the types of safety relief device is the frangible disc assembly, where copper is used as one of the ruptured disc. There, once critical pressure is reached inside, it ruptures and vents the gases and prevents the major, probably some collateral damage. Coming to the Avogadro's hypothesis says that equal volume of gases will occupy or will give equal number of particles, or will have equal number of particles at standard temperature and pressure. So, when molecular weight is expressed in grams, it is called as gram molecular weight. So 1 gram molecular weight of a gas contains 6.023 multiplied by 10 to the power of 23 molecules. And this is called as Avogadro's number. So the Avogadro's hypothesis also can be expressed as 1 gram molecular weight of any gas will occupy 22.4 liters of volume. So let me give you an example for this. The helium and nitrogen. See, the molecular weight of helium is just 4, and expressed in grams is 4 grams. And the molecular weight of nitrogen is 28. Though the molecular weight of nitrogen is 28 and molecular weight of helium is 4, they have the same number of molecules and they occupy the same volume of space. Now, how do I apply for my anesthesia practice? See, nitrous oxide is a liquid gas. Why it's a liquid gas? Because of its critical temperature. The critical temperature of nitrous oxide is 36.5 degrees, and below this critical temperature, nitrous oxide will remain as a liquid gas, and above it, it cannot remain as a liquid. So, whereas oxygen, the critical temperature is minus 118 degrees centigrade, and always at room temperature, it remains as a gas. Now, the pressure gauge of nitrous oxide will always read same 745 psi. That is the vapor pressure of nitrous oxide till the last drop of nitrous oxide liquid is present inside. So by opening the nitrous oxide, we will not be able to know how much of nitrous oxide is available for us to use. So how do I know how much of nitrous oxide is there in the E-type cylinder? So again, the application of Avogadro's hypothesis. For that, I have to know the molecular weight of nitrous oxide. You know the molecular weight of nitrous oxide is 44. That means 44 grams of nitrous oxide will give 22.4 liters of the nitrous oxide vapor or gas. So now, if I want to know how much of the nitrous oxide I can use it from the cylinder, I have to weigh the cylinder, and to know exactly how much of nitrous oxide weight is there, I'll have to minus the tare weight or the weight of empty cylinder. So once I minus from the total weight, the tare weight, I'll get what is the actual weight of nitrous oxide liquid that is present inside the cylinder. So that is usually the E-type cylinder, when it is maximally filled, it will have about roughly 3.3 kgs. So that is 3,300 grams. So that means 44 grams will give us 22.4 liters of the gas. So 3,300 grams will give 1680 liters, but this is based on Avogadro's hypothesis. The standard temperature is always 0 degrees centigrade or 273 kelvins. Now again, use of Charles' law, I know that at room temperature, I'll have about 1,800 liters of nitrous oxide. Suppose if I'm using about 6 liters of nitrous oxide per minute, I can use it for 300 minutes. One more application of Avogadro's hypothesis. Just previously, I was talking to you about sevoflurane, because that is one of the most commonly used inhalation anesthetic agent. So how do I know that 1 ml of liquid sevoflurane will give how much of vapor? Because I'll be using vapor. So for that, I have to know the molecular weight of sevoflurane. So the molecular weight of sevoflurane is 200 grams and 200 and expressed in grams, the gram molecular weight. Now I know that 200 grams of sevoflurane will yield 22.4 liters of vapor. So 1 gram will give me how much of vapor. So that I've already calculated, it is 112 ml. But I have to know how much 1 ml of sevoflurane will give how much of vapor. So 1 ml is not 1 gram. For that I have to know the density of sevoflurane. Density of sevoflurane is 1.5 grams per ml. So 1 gram was yielding 112, so 1.5 grams, that is 1 ml of sevoflurane, will give 168 ml. Again, it is at 0 degree centigrade or 273 kelvins. Using again Charles' law, already we have derived, so 1 ml of sevoflurane will give 180 ml of the vapor. Now, how do I use this for my anesthesia purposes? Now, once I'm using sevoflurane, I want to know how much of this I have to charge the patient. Suppose I'm using sevoflurane for 1 hour. So what will happen? Suppose if I'm using a fresh gas flow of 9 liters and 2% sevoflurane. So per minute I'll be using 180 ml of sevoflurane vapor, that is 1 ml of the liquid. So if I'm using 1 ml of liquid per minute, per hour I would be using 60 ml. So that will be about 1,800 rupees for the patient because 1 ml of sevoflurane roughly costs about 30 rupees. But if I go for low flow anesthesia, so if I go for low flow anesthesia and then I use 1 liter of the fresh gas flow and I'm still using 2% sevoflurane, so then what will happen is per minute my use of vapor is only just 20 ml and per hour it is about 1,200 ml of vapor. So if I want to know how much of liquid sevoflurane I'm using, I would be using only 7 ml. And cost for the patient is 210 rupees. Just you can imagine the economy of the sevoflurane I can use by going in for low flow anesthesia. This is again the application of Avogadro's hypothesis. Coming to the next law, the Dalton's law of partial pressure. The Dalton's law of partial pressure states that, in a mixture of gases, the total pressure is equal to sum of the partial pressures of individual gases. If I want to calculate the partial pressure of a particular gas in a mixture, I have to know the fractional concentration of that gas multiplied by the total pressure. I get the partial pressure of an individual gas. And let me give you an example. Here is a mixture of multiple gases, but I am interested in oxygen. How much of oxygen partial pressure is there when I am breathing room air, probably at sea level, where the atmospheric pressure is 760 millimeters of mercury. So then I have to know the fractional concentration of oxygen. It is same fractional concentration of oxygen will be same 0.21 even if I go to a high altitude area or if I stay in at sea level. So 0.21 multiplied by 760 is 159 millimeters of mercury. This is the PiO2, the partial pressure of inspired oxygen at sea level. So suppose, I was talking just now about the high altitude area. It is always, the altitude and the barometric pressure, they are inversely proportional to each other. You keep going up, so the atmospheric pressure starts coming down. So let me give an example. So suppose in Ladakh. So let us say the atmospheric pressure itself is 400 millimeters of mercury there. And 0.21 is still the FiO2 or the inspired oxygen concentration there. So 0.21 multiplied by 400, the partial pressure of oxygen in that air it will be about 84 millimeters of mercury. That is almost half of what I would be inspiring at sea level. So that is the reason if a patient or if a person suddenly goes to a high altitude area without acclimatization, the chances of severe hypoxia followed by pulmonary edema can be very high. Coming to the next law, Henry's law. So Henry's law says that the amount of a gas dissolved in a unit volume of a solvent is directly proportional to its partial pressure. So to know exactly how much of a gas is dissolved in a unit volume of a gas, you have to know the solubility coefficient of that gas and the partial pressure. So let me give you an example of the blood. In blood, oxygen is transported in this thing is with the hemoglobin. The other is in the dissolved form. So with the dissolved form, how much of oxygen is always there? To calculate that, I have to know the partial pressure of oxygen. So partial pressure of arterial oxygen when I am breathing room air at sea level, of course, will be roughly about 100 millimeters of mercury. So 100 multiplied by 0.003 will be the dissolved oxygen will be about 0.3 ml per 100 ml of plasma. So how do I apply this? Because majority of you, when you are asked about how do you treat spinal hypotension after spinal anesthesia, you always say first thing is going to give 100% oxygen to the patient. How 100% oxygen delivered to the patient is going to improve his oxygen content. Because in oxygen content, two things are there. The oxygen combined with hemoglobin, other is the dissolved form. We are not going to increase the oxygen content by increasing the amount of oxygen that is combined with hemoglobin. But we are going to increase the amount of oxygen that is in the dissolved form, because I'm going to increase the PaO2 to 600 millimeters of mercury once I give 100% oxygen. So now the dissolved oxygen content from 0.3 ml, it goes to 1.8 ml, that is per 100 ml. So now the blood volume is roughly about 5 liters. So total amount of oxygen that is dissolved will be 90 ml. So that should be able to increase the oxygen content and look after the brain ischemia. Another is the hyperbaric oxygen. That is another application. Suppose, let us say that one of the applications of hyperbaric oxygen is severe anemia. Let us say that the patient is severely anemic. If I push him into an hyperbaric chamber and then provide oxygen, 100% oxygen at 3 atmosphere, so then I can increase his partial pressure of arterial oxygen to 1,800 millimeters of mercury. That is 3 times his PaO2 with 100% oxygen at sea level. So now the dissolved oxygen content will be 5.4 ml per 100 ml. And in roughly 5 liters of blood, it can be 250 ml of oxygen. Now, theoretically speaking, this patient doesn't require any hemoglobin at all, because I'm giving him 250 ml of oxygen in the dissolved oxygen content. 5 minutes more. So coming to the other gas laws, I don't know how fast the time has gone. So we have the laminar flow and turbulent flow. So the laminar flow is always by Hagen-Poiseuille's law, and turbulent flow by Graham's law. The Hagen-Poiseuille's law says that the flow is directly proportional to the pressure gradient and 4th power of radius, and inversely proportional to the viscosity. So what are the applications of Hagen-Poiseuille's law? Suppose if I want to give fluids fast, I just have to increase the height so that I am increasing the pressure gradient. And we always advise for maximum sized endotracheal tubes to be used so that the flow can increase, the resistance can decrease, because flow is directly proportional to the 4th power of radius. Again, the same thing with IV fluids. And if I want to give blood transfusion, I'll have to use a higher grade, that is at least 16 gauge or 18 gauge IV cannulas. The same thing with, if I want to give fluids fast, it is better to go for a peripheral cannula rather than a central vein, because the length and flow are inversely proportional to each other. The same thing with viscosity, the blood flows slower. And in a tetralogy of Fallot's patient, because of erythrocytosis, the viscosity is high, the blood will not be moving faster, there is always a chance of thromboembolism. Then the Graham's law is flow is inversely proportional to the density. So, based on the Reynolds number, the laminar flow, once the Reynolds number crosses 2000, the laminar flow can get converted to the turbulent flow. So especially use of Heliax is one of the applications here. So whenever a patient has an acute exacerbation of COPD or the bronchial asthma, what will happen is the bronchi and bronchioles will become narrow, more turbulence occurs. Once the more turbulence occurs, the flow decreases, the patient has to increase his workup breathing. Suppose if I, instead of air, I use Heliax. So, the Heliax, the density is 0.4 when compared to the density of air as 1. So naturally, the patient's the workup breathing, the resistance offered is much less. The last one for today's talk is the Bernoulli's principle. You know that when gases are passing through a tube, when they encounter narrowing, what will happen is the pressure drops, the velocity increases. That is the Bernoulli's principle. Suppose if you add another gas there at the place where there is narrowing, so because of the decreased pressure, the entrainment of the second gas will occur at that particular level. So what are the applications? One is the Venturi mask, and which is a fixed performance device. Another again in Rager workstations, instead of a second stage pressure regulator, they have a flow restrictors. And third is the integrity of the inner tube of the Bain circuit. We always go with the Pathic's test, which is again governed by the Bernoulli's principle and Venturi effect. So just to conclude, we use a lot of gases, and these gases definitely obey gas laws, and the knowledge of these gas laws will make us more safe for the patient. These are some of the references. Thank you very much.
Thank you, sir, for that. We can take the questions at the end of the session. Thank you, sir.